All right, this is Math 2, Unit 3.6, Worksheet K. We're looking at congruence in right triangles. All right, working on some proofs here. First of all, I have a couple given statements. I'm going to go ahead and copy down what they gave me. They began by saying that angle WVZ and angle VWX are right angles. That's given, and it's already marked here as right angles. Great. They also told me that WZ as a line segment is congruent to VX as a line segment. So WZ, which is this long one here, is congruent also to this long one here. Alright, so those are congruent as well. Now, we have a given reason of the reflexive property of congruence. The reflexive property of congruence is a lot like when we had before, when we would have a triangle and then another triangle, and we would say this line is reflexive property because they share that same line. Same is true here. These triangles all share this line. This one uses it here, there it is, and this one uses it here, there it is. So what they're basically saying is that VW or WV, whichever you want to go, is congruent to the other way. So that is congruent to that. So at this point now, we have right angles. We have a right angle and a right angle, and we have an equal line and an equal line. If I broke this up into smaller parts, what it would look like is I have this triangle is equal to, that's this one here, is equal to this triangle if I separate them. And we said that that was that equaled, and we said that these equaled each other. And so what I have is I have the hypotenuse, which is the angle across, the line across the right angle. That's my hypotenuse. And a leg is one of the other sides. I have a leg here. So in this case, I can now say that triangle WVZ is congruent to triangle VWX by the hypotenuse leg theorem. Oops, I lost you again. Sorry about that. So again, WVZ is congruent to triangle VWX by the hypotenuse leg theorem. Okay, so it shows some congruent statements, and that's how that works there. Let's look at exercise 1. If the measurement of angle X, this guy here, is 54, what is Z? Well, if that one is going to be over there and that one's going to be over there, we've already have the 90s in those spaces there, and so we know it's not those, and so we know it's not 90. We have what's going to be equal to it. There's similar triangles, similar spaces, so it's going to be equal to 54 degrees. And then if it's 54 degrees in angle X, then what is VWZ? Where did V go? VWZ. So it's asking what is this one, what's left of it. Well, what's left of this one is what's left of this one as well. And so we do a little bit of math and say, well, what's left is 90. So we go with 90 minus 54 to find out that, oh, what's left is 36 degrees. That's all I got because I already used a 90 in the corner. So I used a 90 and I had a 54, so my third angle left is going to be 36 degrees. Okay, study exercise 1. Can you prove that WVZ and WVX are congruent without using the hypotenuse leg? Yeah, you probably could if you use Pythagorean theorem. If you found another pair of congruent sides, you might go side, side, side with it. So there's some different ways to do it. You might need some more information, but yep, it's very possible. Okay, let's move on down to these ones, some more of the fun ones. Okay, we have to find the values of X and Y. Yep, here we go, find the values of X and Y. These are triangles that are congruent by hypotenuse legs, so I have to find out what X and Y are. So I have X minus 4 over here. I have an X as the hypotenuse part. On this triangle, I have a 2Y, and down below on the leg, I have an Y plus 3. The way I would set this one up is I would start looking at the parts, and I want to solve for one of the variables if I can. I want to basically do some substitution method is how I'm going to look at this one here. So when I look at the hypotenuse, that's pretty much the easy one to look at here. I can say x is equal to 2y. And because x equals 2y, now I can take a look at the legs, set them equal to each other. I can do x minus 4 equals y plus 3. And I can take the value of x, which is 2y, and plug it in there. And now I have 2y minus 4 equals y plus 3. I'm going to subtract a y from both sides. So I have y minus 4 equals 3. I will add 4 to both sides. So now I have y equals 7. So I'm doing okay. I have a value for y. Now I need to make sure I have one for x. And we said that y, if y was 7, x was 2 times y. So what is 2 times y? X is going to be equal to 14. There's my values for x and y. So a little substitution and plugging things back in and working it out. So there we go. Number 6. For number 6, I did this one, and you know, when you first do it, you're trying to figure out, okay, what do I substitute? Do I start with the y plus 5 and make that equal to 2y minus x? Do I do the bottom over here and do y plus x equals x plus 7? Which way do I go? I'll tell you what I did. I looked here and I said, you know what? If I make those equal to each other, if I make y plus x equal x plus y, the x's are going to cancel each other out, right? If I subtract an x from here and subtract an x from here, it goes away. So what am I left with? Y equals 7. That wasn't too bad. So there's one value, y equals 7. Done. Now let's plug that back in to one of these other guys to figure out what it could be. I'll use this one now, my other set of numbers. So y plus 5 equals 2y minus x. Let's solve for x with my other equation. Plug 7 in, so 7 plus 5 equals 2 times 7 minus x. So 12 equals 14 minus x. I don't like having negative x's, so I'm going to add x to this side. So I have x plus 12 equals 14. I will subtract 12, and x equals 2. And that's it for number 6. I have y equals 7 and x equals 2. All right, on the bottom part down here, it says the LL theorem says that two right triangles are congruent if both pair of legs are congruent. What theorem postulate could be used to prove the leg-leg theorem is true? With a leg-leg theorem, what you're basically saying is I have a leg, and I have another leg, and if I have a leg and a leg, two right triangles are congruent. If that's congruent to that, then I could say they're a triangle. The theorem that would probably help that there is if I could find this angle, then I could use a side angle side, and then I could prove that they're congruent. That would really help. I don't have it, but if I did, then I could really prove that that was actually true. Okay, let's look at the back side. Looking at number 8, starting out first of all, it says what additional information would prove each pair of triangles congruent by the hypotenuse leg theorem? In this case here, they gave me a leg and a 90 degree. I think it'd be really helpful if they gave me the hypotenuse. If they told me that AC was congruent to DF, that would probably help, but they didn't. Over here, I have a leg, I have a hypotenuse, as far as I know. What I don't know is that actually a right angle? They need to tell me that angle M and angle S are right angles. If I don't know that, then I don't know if I can use hypotenuse leg. Yes, they look like right angles, but if it doesn't tell you, don't assume. Okay? Number 10, I have a side, and this is the hypotenuse because it's across the 90 degrees. What I don't have is a leg. I need a leg. It doesn't matter which one it's going to be, and it could be, they could tell me that LK is congruent to ON, or they could tell me that LJ is congruent to OM. Doesn't matter which way they go, I just need to know that something is going to be congruent there. Okay, number 11, same idea. I have the 90 degrees, so I'm good. What I really need is I need a leg. I don't need a hypotenuse because the reflexive property, I already know that that's going to be equal, reflexive property. What I need is to know, does this equal that, or does this equal that? So I need a leg here to prove that this is going to be congruent. And again, that could be WZ, double circles, equal to YX, or it could be the long ones, WX, congruent to ZY or YZ. Alright, let's look down at the next one. The next one's a little funky a little bit, but really not too bad actually. Looking at the figure here, we have this crazy figure all over the place. We're trying to work out some paragraph stuff here. So let's complete the paragraph proof that shows that AC and CD are perpendicular. So AC is this line right here. Here's my AC. Okay. And CD, which is here, are perpendicular. Perpendicular is going to mean that what? It makes a 90-degree angle. That's the idea. I got a 90-degree angle there. It sure looks like it is, but how could I prove that it is? The way I can prove that it is if there's slopes. If I multiply the slopes together and I end up with a -1, then it's going to be a perpendicular two sets of lines. Let's take a look at what I have. The slope of AC. AC is right here. Here's my AC. And what I did to take a look at AC, I could do it the long way, but there's some nice little grids here. AC is this line, and it goes down 2 over 1. So the slope of AC, the AC slope is down 2 over 1. Okay, so that's going to be a -2 on my little paper over here. Zoom back out here. -2 is my slope. Now CD, which is right here, this guy here, we're going to go up 1 over 2. Up 1 over 2. So we're going, for CD, we're going up 1 over 2. Well, that's going to be a half. And when I multiply, since the product of two slopes is, well, -2 over 1 times 1 over 2 is a -1. So because I end up with a -1, then the line segments are perpendicular. Okay? Now, how do I know that AB, this guy, is congruent to CD? The way I would have to figure out if AB is congruent to CD is I would have to use, back to one of our early lessons, the distance formula. Yep, that's right. So the square root of y1 minus y2 plus x1 minus x2. And those are both squared, sorry. So I have to use the distance formula, which means I get to do some math. Loads and loads of fun. So if I looked at, for example, AB, from A to B, the value of A is -3, 5. The value of B is 1, 3. So if I use my distance formula, I would do y1 minus y2 squared plus x1 minus x2 squared. 5 minus 3 squared is 2 squared, plus -3 minus a 1 is a -4 squared. Last time I checked, 2 squared is 4, -4 squared is 16. So the square root of 4 plus 16. Square root of 4 is going to be, oh, sorry. Gotta add them up first. Don't do that quite yet. Sorry about that. Got ahead of myself. So 4 plus 16 is 20. can't do that. Square root of 20, I have to look at what multiplies ultimately by multiplication. 20 is 5 times 4 is what 20 is. So the square root of 4 is 2, and I have a root 5 left. Okay, so I have to add these together before I can start playing with it. I can't break them apart or I make a giant mess. So don't do that. I almost made a mistake. So 4 plus 16 is 20. Now I can use multiplication to figure out what I can factor out of that radical. And end up with 2 root 5. That's what I get for AB. You would have to do the same thing for CD, same distance formula. And then when you do that, if CD is equal to that as well, then you would say yes, they are going to be equal. If the distance is different, then you would say no. But you have to do some math to figure that one out there. Okay? All right. And that's about it. Complete the paragraph proof to show that ACD equals DBA. ACD is we already said that ACD is a right angle from exercise 12. You can also use the product, oops, sorry about that again, right angle here. You can use the product of slopes to show that ABD is a right angle, which we did. ACD and ABD share the same hypotenuse. You can use and what goes in here, distance formula to show that AB equals CD, which you'll need to solve that to prove that that's actually true. So don't forget to do it. Therefore, by the hypotenuse leg theorem, ACD is congruent to DBA. So right angle, distance formula, hypotenuse theorem. And you are done. And that concludes lesson 6.